Great to be here to talk to you this evening. I wanted to start by making an observation. These two cars on the screen are the same car, but very clearly they are not the same car. They may both be Fiat 500s, but the vehicle that you're actually getting if you buy a Fiat 500 from the 1980s or from the 2020s is a completely different car. And this is a trend we see absolutely everywhere. And it's not just this anecdotal trend. The data really backs it up as well. No matter where you look in the world, our cars are getting heavier and heavier. Now, of course, some countries are famous for their bigger, heavier cars. You know, the USA springs to mind immediately. Others, such as Japan, are famous for their small cars. But wherever you are in the world, cars are getting heavier. And what I want to do over the next 15 minutes or so is talk to you about why I think that's a bad trend and what we can do about reversing it. But today's also not just about cars, it's about motorsport. So you can see the same trend happening in motorsport series. So here we've got the vehicle minimum weights from Formula One over the last 120 or so years. Forgive me for any experts in the audience. Some of the data from the first half of the 20th century, it's quite hard to deconflict whether it includes driver weight or not, so there's probably 70 or 80 kilos in some of these earlier numbers. But you can see the first cars, such as top left, that's a Mercedes from the 1910s. Big car, 2 drivers. They're quite heavy. And over the following 50 years, cars got smaller and smaller and lighter and lighter. So see the Ferrari in the middle from the 60s, very small, very lightweight racing cars. Since then, we've crept up and crept up. And the current regulation set are one of the few in the last 50 years where there's been a reduction in vehicle weight. Almost every other regulation set has seen an increase in weight, Formula One. But that's not just true of Formula One, it's true of pretty much every motorsport series. So pick your favorite motorsport series. Almost all of them have seen pretty substantial increases in vehicle minimum weights over the last 30, 40 years. So why has this happened? And actually, thinking about this through a motorsport lens is a perfect analog for why this is happening in the automotive world as well. The primary reason is safety. Vehicles have got a lot safer. Crash structures, the halo in F1. You see the image on the top right of the screen. That's Zhou Guanyu's crash at Silverstone a few years ago. He walked away from that car. That's incredible. That, of course, comes at the price of some weight, but I think we all agree that's a price we're willing to pay for that immense safety. Refueling's been banned in Formula One, so fuel weights have gone up. We're seeing power units such as batteries, hybrid technology, that adds weight as well. And also the cars are just bigger. And that's useful for a number of reasons for vehicle dynamics, but also for the aerodynamic platform. That adds a benefit. But that benefit comes at a cost. And I think that's been a bit of a hidden cost over the past 40 or 50 years. The other reason we have heavier cars is people like bigger and heavier cars. So this is data from the USA, but it's representative of the world. And what I would have considered a car made up about 80% of the US car sales in the 1970s. Today, it's sub 30%. And some big brands, such as Ford, don't make traditional cars anymore. They make SUVs, they make pickup trucks, and they don't really make cars. So us, as consumers, have been driving this push towards bigger cars because it's what we want, what we demand. But these things have come at a cost. And I got started on this by looking at this vehicle. And I just thought, intuitively, this car cannot be an environmental benefit. But it is badged and sold, at least in California, as a zero-emissions vehicle. And it comes with government subsidies because of that. You can't buy it in the UK, so that doesn't apply to the UK. But intuitively, this can't be the solution to our transport sustainability. So I want then to pose a thought experiment to you all. We know that cars are getting heavier, and I'm going to assume a sort of goodwill from the consumer, that people want to do the right thing. Clearly, there'll be some edge cases where that's not true, but in general, that's true. So let's ask the question. If you could know only one single piece of information about the total environmental impact of your vehicle, what would it be? Now, of course, given where my talk has started, the answer is perhaps before the question. But nevertheless, it's worth exploring it. And I think we also need to ask ourselves the question, is this even possible? Because clearly you cannot create some sort of rating or index system to balance everything, right? There are too many variables, and it's about what you would prioritize. Do you care about the CO2 emissions from your vehicle? How do you use your vehicle? There are so many variables, it's impossible. However, is there something that's good enough? So, to skip ahead to the answer is clearly mass. And if you want me to sort of show my working, come and ask me afterwards, because I could bore for Britain on the subject. But I think if we know that the answer is mass, we can sort of think about it at a very school level. We know that work done is force times distance. I think there's an analogue for us to explore here, which is that the environmental impact of our vehicles is going to be the mass of that vehicle, its weight, multiplied by the annual distance that you drive it. So let's just give this a little test. So with my colleague Nick Molden, who's another Oxford graduate who works for emissions analytics now, we tested just over 1,000 vehicles. These are internal combustion engine vehicles, so hybrids, petrols, diesels, all that sort of thing. Looked at their weight and looked at their CO2 emissions. These are real-world CO2 emissions, not from test cycles or anything. And you can see that while there's huge variability in classes, driven by whether or not they're hybrids and things like that, there is a strong trend that the heavier the vehicle, so the right-hand end of the graph, the higher the CO2 emissions. But it's not just true of internal combustion engine vehicles. It's also true of electric cars. This is some data looking at energy consumption from a wide variety of electric vehicles, and perhaps unsurprisingly, the sort of e-bikes and scooters have incredibly low energy consumption and low weight. But once you kind of move out of that category into things that you might reasonably call a car, you'll get quite a nice linear trend between the mass of that vehicle and its energy consumption. That's not necessarily surprising, but it just validates the argument that as we use a vehicle, its energy consumption is going to go up with its weight. But also, if you think about it, that's also going to be true of the life cycle impact of that vehicle. Of course, there'll be differences between classes of vehicle, but as you increase the amount of stuff that goes into a vehicle, the emissions associated with that amount of stuff are also going to go up. Now, we talked about safety in F1. What about safety in vehicles? And here's where you kind of get a real diverging set of outcomes. If you are in a heavy vehicle, that's very good for you from a safety perspective. If you are hit by a heavy vehicle, that's pretty bad for you. So it's a classic example of an externality, that what's good for you is bad for everyone else. And these two graphs illustrate that. So the graph on the left shows the risk to the driver with the mass of the vehicle that you're in an accident, and you can see the decreasing trend. The one on the right shows the relative risk of mortality against the mass ratio of two vehicles hitting each other. So if the mass ratio is 2 on the x-axis, that means the vehicle that hits you is double the weight of your vehicle. And you can see that if the vehicle that hits you is around double the weight of your vehicle, your chance of dying in that crash is about 10 times higher. So it's a really, really classic externality. And so the logical thing for me to do then is, if I'm buying my next car, I need to buy this. It will be incredibly safe. Not so sure about the fuel economy on this, though. So moving beyond safety, let's think about infrastructure. Potholes are the bane of everybody's life. It's the day of the local elections, and potholes have been flying through my letterbox with alarming regularity in the recent weeks. The thing is, potholes aren't an abstract thing. They're caused by vehicles driving over roads. The heavier the vehicle, particularly the axle weight, the more likely a pothole is. Our vehicles have got heavier. That is clearly a reason why we're experiencing more potholes. Similarly, this is Hammersmith Bridge in West London. It's been closed for 7 years. I'm sure the local elections around there are dominated by this topic. One of the reasons it's shut is because this was a bridge designed in the late Victorian times for horses and carts. We've now got incredibly heavy cars going over it. Our infrastructure isn't built for these heavy cars. Our potholes, our roads. This photo on the left is from St Aldate's. You can see that bus stop, big heavy buses turning their wheels, has been resurfaced 4 times. And finally, do you struggle to find a parking space? Do you struggle to fit your car down your road? Again, the standard width of a British road is 7.5 metres. In the late 19th century, that was enough to park a car on both sides and drive 2 cars down the middle of the road. Today, if there are 2 parked cars on either side of the road, you struggle to fit a single car down the road. Our infrastructure is not built for these cars either. And finally, I remember playing with Lego when I was a kid. Lego looked like it did on the left. We have become so culturally inculcated with bigger, heavier vehicles that Lego has had to get wider. It's seeped through the whole of society to accept bigger, heavier vehicles. And I think there are very, very good engineering reasons that I hope I'm demonstrating why that has to change. And here's why today is a great time to fix this. So, vehicles are electrifying, right? We've got amazing battery electric vehicles coming onto our roads today. The UK fleet is rapidly changing. This means we're using less petrol. However, for a government, that's a bit alarming because it means they're taking less revenue in petrol tax. You may think of that as a good thing, but I can assure you that governments don't think of that as a good thing. So, and indeed, petrol duty has actually been, the revenue from it has been falling in real terms since the middle of the last decade. So here's an idea. Let's get rid of road tax and petrol tax. Cheers around the room. However, on a revenue-neutral basis, let's replace it with a mass times distance charge. Immediately, you can start to shift the basis for our taxation onto a parameter which, okay, it's not perfect, but is a really good surrogate for the environmental impact of our vehicles. And in fact, if you think about the 3p per mile EV charge that's come in, that's about what you would expect if you're going to start to phase this in with the proportion of battery electric vehicles in the fleet over the next 20 or 30 years. So I think things are heading in the right direction. So let's just run it as a little calculation. So to work this out, I think you need these 4 parameters. You need to know the average mass of a vehicle in the UK. You need to know the average annual distance that it's driven, the total number of vehicles in the UK, and the tax revenue. So last year, we raised about 40 billion in taxes on vehicles. So you can work it out. You can say that the annual tax will be the mass of your car divided by the average distance you drive divided by the average times by the total tax revenue raised divided by the number of vehicles taxed. So I just put together some examples from kind of common vehicles you've got in the UK with a kind of indicative mileage that you might drive. And the tax under the existing system is a combination of the annual tax. So this doesn't include the higher tax you typically pay in the first year where you acquire the vehicle. And hopefully in this table you can find something that might approximate the car that you drive and the distance that you travel. And you can see there are winners and losers. The ones I'd particularly like to highlight are if you have a heavy car and you drive it a long way, like a Tesla Model Y, you're going to start to be paying quite a lot more tax. If you have a sports car, like a McLaren 720S, and you don't drive it very far, you're a big winner. And that's going to be a big change, right? Because that's perceived as a luxury. And maybe, we shouldn't politically accept that. But the environmental impact of that vehicle, not driven very much, is low. And so should it be taxed highly? That's a question for politicians rather than engineers, but that's how this shakes out. So to conclude this bit of my talk, I think I can argue that vehicle mass is the single best predictor for the environmental impact of vehicles. And now we're in this diverse powertrain world where emissions are no longer linked just simply to putting the petrol or diesel in your car. We need to move on and we need to update our taxation system to account for this so that we can start to wind back the really damaging trend from the last 15 years or so of heavier vehicles. And I think good enough, rather unattainable perfection is what we should aim for. But in the last 5 minutes or so, what I'd like to talk about is 2 fantastic undergraduate student projects that are linked to this area, but not directly linked to vehicle weight. So the first is a project from a student last year, Will. Many of you will know that in Oxford we've been lucky enough to see about 160 battery electric buses deployed on the roads. Many of you will have ridden on them at a cost of about £82.5 million. And these buses don't do some of the long distance trips, to London or the airports or whatever. They're what we call the Oxford Smart Zone. So they go out to places like Kidlington, but they don't go as far as Abingdon to kind of calibrate where these vehicles go. And what this project was interested in as part of a bigger project was what the noise pollution implications of these buses were, and also what the air pollution was. And Will's part of the project in particular measured the noise using, he brought a prop, one of these devices. So these are called audio moths. They're a spin-out from computer science department here at Oxford. And these are noise pollution instruments. You can leave them on lampposts. They run on 3A batteries. Fantastic for something like a 4YP. And so here's what Will found. We measured the noise from before when the buses were deployed and then after, at a number of locations in Oxford, you can see on the map, many of which are sort of what you could call along the central bus corridor for running from St Aldate's down to the Plain roundabout, where there's a very high level of bus traffic and relatively few cars, and then some control locations in Oxford where there are no buses, but still cars and other things that affect noise, right, such as wind, rain, all these other things that affect the noise profile. And what Will found was that depending on what location we measured, there was an average 5 decibel decrease in urban noise, whereas at the control locations, for whatever reason, particularly weather dependent though, there was around a 7 decibel increase. Another part of the project also found there was a 24% reduction in nitrogen dioxide at bus locations. So this change from diesel buses to battery electric buses has led to these noise and these air quality improvements in Oxford. And of course, you can also strap these audio moth devices to the buses themselves. And you can find that when the vehicles are off, perhaps to my relief, the sound profiles are very, very similar. But when the vehicles are on and running, the electric bus is sort of 20-ish decibels quieter than the than the diesel bus. So fantastic set of improvements for the sort of Oxford urban soundscape. The last one I wanted to choose to highlight to you today is life cycle analysis. So this is a project from Alfie, and there are different approaches to life cycle analysis. This is particularly when applied to electric vehicle charging. You could take an average of the grid intensity. You can sometimes use marginal. People who want to sort of give negative views on carbon emissions can do that. But today we have data. You can go and find out what the carbon emissions from the electricity grid are today, right now in Oxford, online. And so there's the link to do it yourself. This is just a screenshot I took a couple of days ago. And we use a statistical method to say, if I plug my EV, or indeed my phone in right now, here is how much the carbon emissions from that action are. And then we can work it out for all of Europe. So this is the work that Alfie did. And you can sort of strum up some scenarios. But the message is that across Europe, it is almost always favorable, unless you live in some far eastern countries of Poland, Czech Republic, and so on, to switch from a battery electric to a battery electric vehicle. However, in some cases, that change is quite marginal. It's of order a few light bulbs, rather than a massive improvement in some countries. But if you live in the Nordic countries, it's a fantastic improvement. And this project won an international ASME prize as well. So congratulations to Alfie for that. So I'd like to conclude by just acknowledging Will and Alfie on the left, Nick, Pat, who's a visiting fellow, Martin, who's in the room today, Tristan and Kelly, a visiting professor, all the people who've collaborated on these projects today. And of course, I've written some books on this subject, which you can buy in all good bookshops. And I'd be very happy to take your questions. Thank you very much for your attention.